Hey, Algebra 2, welcome to 6.2's lesson from our big ideas titled The Natural Base E. So this is something, it's a new concept that you'll see in this lesson. We're going to define and use the natural base E. We're going to graph natural base functions, so functions with this natural base E in them, and we'll see if we'll solve a couple of real-life problems. But first, let's look at a little cartoon. This is a In the Bleachers cartoon by Steve Moore. It said, Ernie, pluck yourself. We're skins. As you see, the duck is plucking himself. If you know anything about pickup basketball, you'll probably find that funny. Okay. Okay, so on the top of 161, you'll see your vocabulary, natural base E. And so here's what we can kind of write for that. It's a special number, and you can say that. You can say it's a special number like pi or the I, our complex one here. So it's a special kind of number that we notate. Now we know pi is 3.14, but it keeps going and going and going, of course. We rounded to 3.14. So the natural base E is a function that's that is basically comes from an exponential kind of function here. So you can see that that's also written there on your core concept right there on 161. And this kind of explains it here. It shows you the graph of this as it kind of comes up. It gets closer and closer to this line, this like asymptote line, which would be the E line. And you can see as we start to plug numbers in here, if we plugged in these numbers, which would be 10 to the first, if I put that in here, which would be 10. If I put 10 in here for x and then simplify that, I would get this number. If I put 10 squared in, that would be 100. If I put 100 in, that would give me this number. And you can kind of get the idea and the pattern going. But what you want to really see here is that it keeps getting closer and closer to this number 2.71. 2.71. It really gets close to that. So that's kind of what we round it off to. Typically, we would say the natural base E is about 2.71, or some people just say 2.7 would work, or 2.72 if you rounded it to this hundredth. So here's what you also can notice here. I'll just kind of quickly go through. I don't have to do it just with 10. You can do it with any base number here to get this natural base E, just using this little kind of formula really for the E function. So the natural base E uses this expression, this exponential formula. So we could do it with 5. So if I said 5 to the first power and I plug that in, 5 to the first is 5. So I plug in 5 into x in both places and then simplify using my calculator. So I'd figure out, okay, 1/5 and then add 1 and then raise it to the 5th power. That would give me this decimal here, 2.48 and so on. And then I can do it with 5 squared, and I can just keep doing that. That would give me 25. That would give me a decimal that gets a little bit closer to my 2.7. And then the next one, 5 to the third, that's going to be 125 going in for x. That gets me a little closer now to my 2.7. As you can see, there it is at 2.7 now. And then we get to 5 to the 4th. It does the same thing, gets closer. 5 to the 5th gets even closer to 2.71. Just keeps getting closer and closer. Oops, I went back too many times. Okay, so here we are back on this right screen now. So yeah, you can just kind of see how that works. It just gets closer and closer to the 2.71 as we plug it into this, and the graph gets closer and closer to that number, that E number. Now that's a decimal number, it's an irrational number. It just keeps on going and going and going forever there on this decimal. It doesn't stop at this number, it could keep on going. So that's why on this core concept you can see that. There's the 2.71. You might want to kind of highlight that or underline that part. That's kind of what we round it to. Or you can just say 2.7 is what we're going to really see this as. So on your vocabulary you can kind of write that. It's a special number that equals approximately 2.71. And so you can say that for the natural base E. Okay, so now if you go to page 162 on the extra practice, kind of the middle of the page, it says simplify the expression for 1 through 4, and these we're going to do just like we did in chapter 5. So we can just pretend the E is a variable and E is just like x. So it'd be just like if this was an x in this one. So for the first one, we're just going to add the exponents, which we have to subtract, because -9 plus 12. So we'll see e to a -9 plus 12. And that would just give us an e to the third power. So there's that simplified. So we're just, again, doing this just like if it was an x. Over here we would see we're going to simplify the 25 over 35, so 5 can go into both of those. We can simplify that to a 5 over 7, and then we would have to subtract the exponents here on the e, so we can do this and see that it's going to be 5 on top. We'll keep the 5 on the top, and I'm going to move the smaller one down to the bottom where the bigger 7 is. So that way I'm going to say 7 minus 2 at the bottom for the e, so I have 7e to the 5th now on the bottom. So it's 5 over that 7e to the 5th for the simplified form of our number 2. On number 3, we have a couple things going on here. We have a power to a power here. So we're going to have to raise, this here to the 5th power. So really 2 to the 5th power and also this to the 5th power. So when you think of 2 to the 5th, that's 2 times itself 5 times. That's going to give us a 32 right there. And then we're going to end up seeing multiplying this. Negative 3 times 5, that's going to be negative 15. So we're going to see that there happening. So we can kind of see on this one, first of all, that's why I'm showing this in separate things. We're seeing the 2 to the 5th, and now we're going to see this being multiplied here to get what we need here on this one. So that gives me our 32, like I said, from 2 to the 5th, and negative 3x times 5 is the negative 15x. That's just for this first part. Then we're saying times this 2e to the x plus 1 now with this. So now we have to do that. So we're going to multiply these. We will multiply the 32 times the 2. That gives us a 64 for the big number in front. And then we're going to be adding the exponents here. So it's kind of like just combining like terms then with the exponents. And so what we would get there is 14, negative 14 plus 1 for the exponent. So there's our 64, the e, and when we add these together, I'm actually going to take 1 away from negative 15 to give us a negative 14x plus the 1, just combine like terms here on the variables. And then for number 4, we have this fourth root. So we can kind of separate this out first of all, because 16 is a perfect fourth root, so we can kind of do that first if we want to. See that as the fourth root of 16, and then the fourth root of the rest of this with the e to the 24x. And we know that fourth root of 16, that should be 2. What we can do here is change this back kind of into a fraction exponent. So what this could be is the denominator of that exponent will be 4, just like we saw in the last chapter. And 24x, that's like the extra exponent. That would be your numerator for the exponent. So we have e as the base, 24x over 4 will be the exponent that we'll see. So here's our 2 from this fourth root of the 16. And then we have the e, and the exponent for e is now 24x over 4. We can then reduce that 24 over 4 to be just 6. 4 goes into 24 6 times, and so there it is, 2e to the 6th power. Okay, so we're now going to get into the graphs of these natural base e functions, and they're going to be exponential functions, as you're going to see exponential growth, and you're going to see exponential decay just like we saw before. So from the left to right, if it's going up, it's growth. If it's left to right coming down, it's decay. And the function's going to look like this, e to the x. You're going to see the e as the base in here. And you'll notice that the growth one has e to the x, the decay one has e to a negative x. And so that's why I wanted to write it over here like this, to show you that if we have a negative exponent, that would flip the e upside down. And so this is the same thing as saying 1 over e to the x. Because remember what we saw before is that when your base is greater than 1, it's going to grow, which, e is greater than 1. 2.7 is greater than 1, so that would grow, e to the x. But e to the negative x, we're going to see that. We're not going to see this, 1 over e. We probably won't see that. We'll most likely see negative exponents now. So when you see a negative exponent with the x here, that's going to tell you it's decay. So that's how you can kind of tell the difference when we're doing these natural base functions. If your exponent is positive for the e, then it's going to be growth. If the exponent is negative for the e, it's going to be decay. Okay, so 5 through 8, we're going to be telling whether the function represents exponential growth or decay, and then graph the function. So that's the easy part, is just telling whether, and it's actually really quick to do as well. So we can just see when it's a negative exponent, it's going to be decay. When it's positive, it's growth. So our first one, number 5, we can see that's decay. So I'll put D for decay. We know this one's decay on this one, number 5. Number 6 is going to be growth, 4x here. It's positive, so that's going to be growth. This one's got also a positive exponent. Remember, it doesn't matter the number, as long as it's positive, it's growth. So this one's going to be growth as well on this one. This has got a negative 3x for the exponent, so it's going to be decay on that one. So we're looking at it a little differently when we're doing the natural base e functions for deciding whether it's going to be exponential growth or decay. We don't look necessarily at the base number. We now look at the exponent and see is the exponent positive for growth and negative for decay. So on our first one, number 5, let's go ahead and graph this. We're going to put down some numbers here. I'm just going to say -1, 0, and 1. And for the most part, that's the numbers you kind of want to use unless you have something that you need to change them a little bit. We'll see a couple of these we might need to change on this. But if I plug -1 in for x here, negative times -1 will actually be +1. So it's like saying 2 times e, and e again is 2.71. So if I just multiply 2 times e, that's going to be 5.42. And if I plug in 0 here, -0 is still 0. So anything to the 0 power, even e, is still going to be 1. So it's like saying 2 times 1, which is just 2 there for the 0. And if I plug in 1, well, that's going to give us a -1 exponent for that. So it's really going to be 2 times 1 over e, because we would flip the e upside down. It inverts it. And so it's, we want on the calculator 1 divided by 2.71 and then times 2. That would give us this decimal of 0.74. And so then we just plot these points on the graph, and you can see my graph here. You can go ahead and draw it like this. In fact, I think most of them are going down through the middle. This one's got going up the second box up. Go ahead and draw your x-axis. But everybody else here on 6, 7, and 8 is going to be on just the first box. And on this one, we're just going to go by 1. So this is going to be 1, 2, or -1 is here. So we'll just see our graph like this. So here's our -1, and we're up at 5.42. And there's going to be 0 and 2 right there, and then 1, and they're at about 0.75-ish right there. And it's going to be a decay. We know it's coming down as it comes down. Our asymptote here is going to be the x-axis. That's another thing we need to talk about is these asymptotes. We can't forget about them when we're doing exponential functions, because remember, they're like the Superman ride graph. They're very important to remember. It would be like the platform where the people get on and off. You can't collide into that or touch it. So we got to remember that on all of these, it's going to be still the x-axis is that asymptote. So that these are all going to be that way. We're going to see a few in a minute that are not going to be that. They'll change a little bit. All right, number 6, just real quick, let's look at the ones we'll plug in. The only one I'm changing, I'm going to add in a half on this one. You'll see why as we do it. So we plug in -1, so that's going to be -4 here for the e. So we'll see that that's going to be that 0.75. And if I flip this upside down and then raise it to the 4th power, well, we can do that. You can again multiply, or I should say divide 1 divided by 2.7, and then raise it to the 4th power, then multiply by 0.75 on your calculator. That's what we're doing on these. So just you can work this out on your calculator. So let me just show you on this calculator really quickly, just for this one. I'm not going to do it for all of them, but just so you get the idea of what we're doing here. I'd be dividing first 1 divided by this 2.71 number here. That would equal this big decimal. Now I'm going to raise it up to the exponent of 4. So I'm going to use my exponent button, the x to the y. My exponent is 4, hit equals again. So that gives me that number, and now I multiply it by my 0.75 that's out in front. So times 0.75, and that gives me the number I want here, which is about 0.0139. I'm just going to put on here 0.014, just round it to that third decimal place. If we plug in 0, that makes this 0, so e to the 0 would be 1. That's just going to be 0.75, because 0.75 times 1 is 0.75. If we do the half here, we could say 4 times a half is 2. That's why I did this with the half, because I could then quickly take half of 4. So we have e to the 2nd power. So we're going to square the e. There is even actually an e button on the calculator, and you might want to use that to be a little more accurate. Or you could say 2.7 squared and then times it by 0.75. That would give us this decimal, 5.54. And then our last one, if I plug in 1, that's going to be just to the 4th power now instead of the 2nd power. So e to the 4th power, then times it by 0.75 again, would give us 40.9. This is 40.9 here. So our graph will look like this. And as you notice, we're going by 2's on the x-axis but 5's on the y-axis. So it's a little different on this one, just to be able to kind of fit this in. So here's our numbers. -1, we're going to be -1 right here. We're going to be really close to the x-axis. Then at 0, we're still pretty close to the x-axis right here. So it's not going up very much. And then we go to positive, or should we go to half? Half is like right here. We're going to be up at around 5, a little past 5. And then we go to 1, which is halfway here. It just zooms up to 40. And so you can see this one just took off real quick. All right, so number 7, we know it's growth again. As we do our numbers here, I'm going to use these numbers instead of 1 and -1. I'm going to use -4 and +4. And you'll see why, because we have this 0.25. This is like 1/4, really. So if I was to plug in -4, 0.25 times 4 is actually 1. So this would actually give me a -1 here on this one. So e to a -1 is like 1 over that 2.71. Remember, the negative will flip it upside down. And so 5 times this now as a decimal would just be 1.85. If we plug in 0, that's e to the 0, so it's 5 times 1, which is 5. So that's just easy to do always with the 0. If you plug in 4, that's just going to be 1 here, so just e to the first, so it's 5 times the e, or 5 times 2.71, and that would give us a decimal of 13.55. And so now you can see this one's going by 2's everywhere. In fact, it's going 2's on the x-axis, 2's on the y-axis as well. And so now our graph will be here. So at -4 over here, that's 2 boxes this way, we're going to be up about 1.85, not quite to 2. At 0, we're up at 5 right there, and at 2, I should say 4, sorry, over here at 4, we're going to be all the way up at 13.55, so it's approximately up to there, almost at 14. So as you kind of zooming up this way, growth. And then on this one, number 8, we'll just go back to -1 and the 1 with that 0. Always put 0 in here, that's the easiest one to do. So with -1, it's going to make e to the 3rd power. So you'll do e to the 3rd on the calculator and then times it by 0.8. And that would give you a decimal of 16.06. If you do the 0 power, that's just going to be 0.8. 0.8 times 1. Anything to the 0 is still 1. So 1 times 0.8 is the 0.8. And then if we just put the first in there, that's going to be -3. So it's going to be 1 over 2.71 to the 3rd power. So we like this again. So we'd be doing 1 divided by 2.71, then raise it to the 3rd power, then times it by 0.8, just like I was showing you on this one with the calculator. This one's also going by 2's, both x-axis and y-axis. So it'll look like this. Actually, oh, there's my thing. I never gave you the number here. It's 0.04 for this one, really small. This is decay, so it's going to be coming down from left to right. That's why it's higher on -1 and a lot lower on +1. So it's way up here. So at -1, we're going to be all the way up here past this graph a little bit at 16. And there we are at 0.8, so not quite at 1, but almost there. And then at 2, actually not at 2, that really should have been 1. That should have been down here. So I messed up on that one a little bit. So it should have been over here, because 1 actually is halfway in the box there. That's actually 2. But it still is a pretty close curve anyways. All right, let's move on to a little joke of the day. So why do gorillas have big nostrils? You ever thought about that? Why do gorillas have big nostrils? Well, because they have big fingers. That's why. Always a funny one. And a little bit gross too at the same time. Okay, so now we're on 163 at the very top. We're 9 to 11. It says use a table of values or a graphing calculator to graph the function, and we're going to use our Desmos graphing calculator, and we're going to put some values from there down into a table. Identify the domain and range, so we will do that. So that's something that we need to realize. We're going to identify the domain and the range. We've talked about that already. So first of all, number 9, you go ahead and draw your coordinate plane like this here, down the middle and almost across the middle, about 4 boxes up. We're going to go by 2's everywhere, x and y axis. First of all, on this one, you can see the -4 is back behind. Here you have e to the x and then the -4. So that -4 actually is a k number. That's an important number because that's going to be our asymptote number. Our asymptote is not going to be 0 this time, or the x-axis. The asymptote is actually going to be at -4. So let's go over to the Desmos calculator. I'm going to type in e to the x minus 4 on the calculator. So right here, we're just going to type in on your keypad, not here. I don't see any e button anywhere in here, but you can just type in e, and there it is. And then we're going to raise it up, so a to the b raises it up to the x, and then we're going to put a minus 4 in. So we just put minus 4, and there's our function. So here we have it, and we can just kind of maybe see some key points. You can see where the y-intercept is right there. You can see where the x-intercept is right there. So those are just maybe some key points to put down. 0, -3 is on our graph. 1.386 and 0, those are on our graph. So this is what I did. I just grabbed a couple of these key points along this graph, and I put them on a table. So I made this little table just looking at that graph. So there's that 0, -3 point. There's the one for the x-axis. So you have your x-intercept and y-intercept right here. Here's your y-intercept. Here's your x-intercept. And then we have a couple more where I found where it was around at 5, where it was around at 10. So that's what I did there. And then just graph it from here. Now we need to realize that -4 though is the asymptote. So I'm going to put a dashed line down there at -4. There's a green little dashed line right down here. So that's like the platform for ours. And as we can see here, we're going to should be growing. It should be going up from left to right because x is a positive number there, or a positive term anyways. The exponent is. So our graph here on this one goes up from left to right. And so you just can see I'm just mapping out some of those key points. Really -4, over here -4, and it's almost at -4. It's really close to this asymptote by this point. It just scoots along the graph. Number 10, we'll go ahead and do the same thing on this one. Let's come over to 2e, and then x plus 3 is the exponent. So let's come over to our calculator again and put in this one now. So we're going to put in 2, and I'm going to type the e for e button there. And then raise it up to the x. I think, what does it say here? X plus 3. So x plus 3 is the exponent. Oops, put it in the wrong spot. There we go. Let's get it back up as an exponent and then do x. There it is, x plus 3. See, it didn't do it right there. So I think what I'm going to need to do is maybe put that in a parenthesis. So if I open the parenthesis up there we go. And now we got x plus 3, close the parenthesis, and there's our graph. So here we got it, and just again do the same thing, get some key points. There's not really any intercepts here that you can see, but you can see it's, by the time you get to -8, we are nearly at 0 here. Because you can see what's the platform, what's the asymptote? Well, it's still the x-axis on this one because there was no k number. It didn't say plus some number after this, so it's still 0 for the asymptote. And that's how you know if the asymptote moves up or down, is if you do have a k number. So here's the numbers that I just picked off this graph, and you can pick whatever you want. But here's the numbers that I picked. Oops, I forgot to talk about the domain and range. Silly me. So let's talk about that really quick before I go on to that chart there. So the domain for this is all real numbers. In fact, all of exponential growth and exponential decays will be all real numbers. So every time we see the domain on all of these, it's going to be the same thing, all real numbers. It's going everywhere, left to right. But this one's the range. It's only above the asymptote here. It's only above this platform where it's at -4. So y is greater than -4. It's not equal to, because it can't touch it. If it's equal to, remember, the people would die from the ride. So that's our domain and range. Let's go over here now to our chart. So here's the numbers that I picked out from that graph on Desmos, and just put them down in my table of values, about 4 of them. You want around about 4. Again, going 2 every way, so going straight down the middle. The first box is your x-axis. Go ahead and do that, the same thing. And then our asymptote is the x-axis, and as we saw on the graph there, we're just going to highlight a few of these points here, same kind of points as I got up in here, and you can see its growth. And domain and range again. So domain of this one is also the same thing, all real numbers. It will be for all of these. All exponential functions have a domain of all real numbers. And then the range is always going to be a little different, depends on where your asymptote is. So our asymptote's on the x-axis, which is 0. So it's above that, so it's just right there, y is greater than 0. Very simple. Our last one, number 11, let's go ahead and type that into the Desmos, negative e to the x power plus 5. So again, this one's got a k number. We're going to see the asymptote changing on this one. So let's type this one in here. So it starts off with negative. I got to type in my e from my keypad here, and then to the x power right there. And then we're going to just put plus 5 after that. And there's our graph. So there you can see the asymptote is no longer the x-axis. It moved up. And so this looks really strange. It's not, kind of like a waterfall almost. And the reason for that is because of the negative sign. We're going to talk about transformations in the next lesson or two. And that is one of the transformations that we're seeing here. This negative sign is causing this to reflect over the x-axis. Because normally it's going to go up as growth, but now it's going to reflect and it's actually coming down like a waterfall. So really kind of interesting graph on this one. You can see there's your x-intercept 0, 4, or that's y-intercept, x-intercept down here 1.6, around 1.6, and 0. So there's just some key points. You want to get a few key points there, and we'll put those on that table of values. So here's our key points. There's our y-intercept 0, 4, our x-intercept. I grabbed a couple other key points right there, and then we'll just put them on the graph. And again, my dashed line is up here for the asymptote. It's at positive 5. So I'm going by 2s again, straight down the middle for the y, down 4 boxes and draw your x-axis. So this is going 2, 4, 5 is halfway here. So there's my asymptote, and I'm going to kind of come this way and go down. But I want to make sure I put these points on there so I get the kind of right graph. So there's my y-intercept, my x-intercept, and then the next couple points there down below. And I think I put 10, and this should have been negative 10. So I made a little mistake there. That's negative 5. This should have been negative 10 right there. I'll fix that here in just a second. Let's just talk about the domain, which again is the same thing. All real numbers is the domain. Even though it reflected and now it's like a waterfall, it's still going to be everywhere on the x-axis, left and right. And now the range, this will be different. It'll be based off this 5. It's going to be below, as you can see. So we're less than on this one. So y is less than 5. It can't be equal to on any of these because it can't touch the asymptote. So you'll notice that the range will never have an equal to on this one. It'll just be either less than or greater than symbols because we can't touch these asymptotes. We'll never equal them. Let me go ahead and just put this negative sign in here now. This should have been negative there for the 10. All right, let's move on to our next one. So this core concept, which you'll see right there at the top of 162, continuously compounded interest. We've already talked about compound interest in the last lesson, and we were talking about how it's compounded. Sometimes it's compounded monthly, as we talked about. It's 12 times a year, so it's always based on usually years. Daily would be 365 days a year. And we talked about how that was an n number. The n number was, how many times is it compounded or calculated. Compounded is like the word calculated. So if it's like annually, that's once a year, semi-annually, twice a year, and so on. This one now is continuously compounded, which means there is no necessarily time. It's just always happening. Every single second, it's just constantly doing it. So continuously being calculated for interest. And this is the formula here. We kind of call it the PERT formula because it looks like PERT, P-E-R-T. So you have your P is the principal, E is that our natural base E number, and then the R is the rate, the T is the time, A is just standing for the amount, so the A is the amount that we're going to have. And we're going to express always our interest rate as a decimal. So it's going to come to us as a percent. We need to always change it to a decimal, and we need to realize that. Okay, so problem number 12 is going to use that continuous compounding PERT formula. So it says the population of Evans City is currently 48,500 and is declining at a rate of 2.5% each year. You can model the population of Evans City by the equation, and here's our PERT formula where it says P of C is the current population and P of T is the population after T years. So it's using P instead of A here. And the reason why is probably because we're talking about population in this one and not talking about an amount of money or something like that. So So the P of T is the population after 2 years. R is the decimal rate of decline per year. It says predict the population of Evans City after 25 years. Okay, so the first thing we need to realize is that this is declining. This is decay. We're not growing. The population is not getting bigger. The population is actually getting smaller. So we need to realize that this percent here, as we make it a decimal, is going to be a negative decimal number. So because it's declining, this will now be negative 0.025. So as a decimal, we'll move the decimal back 2 places and get the 0.025, but we have to make it negative because it's decay. We're declining. So our rate here, the exponent for the e, will actually be a negative number. So here we go, we're going to put it in. Now I did put a here. I just put a just because of the PERT formula, just so it may be less confusing. Our a, the final amount of the population for Evans City here is a. And then the P from the PERT formula is like the principal, which is the initial amount. P is always going to be in the PERT formula the starting amount, the initial amount. So that's the 48,500. And then we have our E next to that. And then the exponent is going to be the rate. So the rate is there at negative 0.025, and we're going to be multiplying it times time, which is 25 years in this problem. So here's what we're going to be plugging in on our calculator. First of all, we got to figure out what this decimal would simplify to. So multiply these two numbers here. It will still be negative. And so that will give us our big number here, our principal, e to now this negative decimal, negative 0.625. And so now what we can do is we can take the e and raise it to a negative 0.625 decimal number. And once we do that, let's so here we can see, I'm going to try this here. Now it would be so much better if we had the E button. I don't have the E button on this calculator screen. I do have it in the class calculators, but I'm going to show you that in class. But we could still just do this as 2.7, and I actually probably round it. The best to round it would be 2.72. That would be actually giving you a closer estimate than 2.71 even, or even 2.7. So if we say 2.72 for E, and then I'm going to raise it to this exponent, so I'm going to use my exponent button here, and I'm going to put it in parentheses, I got up to make it negative, so I'm going to put open parenthesis here, put the 0.625, and then I got to hit this plus minus button to make it negative, and then close the parenthesis. So now you can see that's what I got up here in the parenthesis, push equals, so that's what that would be, and now I need to multiply this. And let me see if I got that now. Yep, so there it is. So now I multiply this times what we have on the decimal screen or the calculator screen here. And so we times this now by the 48,500 and equals, and that gives us about 25,950. So that's a pretty good estimate. So I made it here. This is actually what the book said, 25,960. So actually, I've probably used the E button. If you use the E button, you get even a closer estimate. We were about 10 people off when we rounded it to 2.72. So the E button will give us even better results. Okay, so we're on the last one, number 13. So we're going to see. Using the PERT formula one more time on this one, so it says your parents will need $25,000 in 10 years to pay for your brother's college tuition. They can invest in an account with an interest rate of 9.8% that compounds continuously. How much should your parents invest today in order to have your brother's full tuition available in 10 years? So for this one, it's going to be a little bit different. First of all, let's figure out what is the rate going to be. It says right here our rate is 9.8%, but as a decimal we want to change that to a 0.098. Move the decimal place back 2 places, and it will be positive because this is going to be growth. We're trying to grow the money, make the money bigger, more. So it will be a growth on this one. So it is a positive number here. So we will use our PERT formula. So this time we know the amount we're trying to get. We're trying to get $25,000. That is our amount. We're trying to figure out how much the principal needs to be. Because it says how much should your parents invest today, which would be the starting amount. What should they start with? That's always the principal. their ending amount is $25,000. That's always going to be the A, the final amount. So as we put this in, 25,000 is going to go where A is, and it's going to equal the principal. This is what we're trying to figure out, the initial amount, times the E, because of its continuous compounding. That's why because it says it's compounded continuously, we're using the E on this one. And then our rate is going to be that decimal 0.098, and then times the time, which is 10 years. So we'll times that by 10. And then we'll just simplify this top here. If I multiply this decimal by 10, it just moves the decimal place back one place. So now it's not 0.98. So that's now we're going to raise it to the 0.98 exponent. So we want to kind of do that. We want to first figure out what is e to a 0.98. We can do that on the calculator like I showed you before. If you need to round it to about 2.72. That would be more accurate. But if you have an E button, that's even better. So what we get there is 2.66 when we do that. E to a 0.98 is about 2.66. And that makes sense because this 0.98 is almost 1, which that's almost around 2.71 there. And then we just got to divide both sides by 2.66. Do that. 25,000 divided by 2.66 on our calculator. That gives us approximately around $9,384 that we would need to invest today. So that's what they would need to invest today in order to get it to grow to about 25,000 in 10 years. All right, so that ends 6.2, sorry. So 6.2's lesson, and I'll see you guys in class.